Hey Royals, in today's lesson, we're going to look at something called mechanical advantage and efficiency. Now, we've discussed a couple simple machines, and each of these simple machines has something known as a mechanical advantage. So it's the advantage that you get by using one of these simple machines because they're designed to help you. So there's two types of mechanical advantage. There's ideal mechanical advantage, which is exactly how it sounds. Ideal. In a perfect scenario, it would be the mechanical advantage that we should get. So if we can remove friction or any other types of energy losses, that's the mechanical advantage that you would get. Now, actual mechanical advantage occurs in the real world. It's the advantage that you get when you actually use this machine. So we're going to look at the difference of these two, and we'll use these definitions to come up with the efficiency of our machines. Okay, so we'll start by looking at the lever. The lever will help us define what we mean by ideal mechanical advantage and actual mechanical advantage. Okay, so if we were to look at this lever, the applied force that I'm pushing down on the right-hand side of my teeter-totter with would be my effort force. That would be the force that I'm applying onto my lever to try to move a load. In this case, my load is the force of gravity acting on this box on the left-hand side of my page. Now, because we're dealing with a lever, there is an arm length from the fulcrum to the load and the fulcrum to where my effort is, and we'll call the distance between the fulcrum and my load dL. And we'll call the distance between the fulcrum and the effort dE. And we're going to use those four definitions of lengths or forces to help us define mechanical advantage. Now, actual mechanical advantage is simply the ratio of the load force to the effort force. So I'm going to call it AMA, actual mechanical advantage. And it's the load force divided by the effort force. And I'll capitalize the F there. So if I want to put it as variables, it would be FL, the load force, divided by FE. Now, with this system, if it's exactly how it is right now, it's telling me that I put in a 155 newtons to lift something that was 285 newtons. So my load force is 285 newtons, and my effort force was 155 newtons. If we divide that, I get 1.8. So it's telling me that my system right now gives me the mechanical advantage of 1.8, meaning I get out 1.8 times as much force as I put into it. So it's allowing me to use a smaller force to move that larger load. Okay, so the actual mechanical advantage is given by this expression right here. All right, so if we look at the law of levers, the law of levers tells us that the force of the load multiplied by the length of the arm on the load side of the fulcrum is equal to the force of the effort multiplied by the length of the arm on the effort side. And this is based off of the ideal mechanical advantage. It tells us that these two things should be equal, but we know from real life that they may not be. So we'll do a little bit of rearranging here, and I can say that the ideal mechanical advantage can be rearranged. I can divide my FEs and DLs and things and make them into ratios, and I can get DFL divided by FE, which looks a lot like my ideal mechanical advantage, should be equal in an ideal world to DE divided by DL. So the lengths of my effort arm to my load arm. So in the absence of friction, or any other energy losses, my ideal mechanical advantage should be dE divided by dL. And so I have here an expression that I can use to identify what the ideal mechanical advantage should be. And I have an expression here that tells me what my actual mechanical advantage comes out to. Because I can measure the forces and know how much force I put into a system and how much I should get out. And then I can go ahead and I can measure the actual lever and get lengths from it and find out what I should get. Now, if I use this definition of the ideal mechanical advantage with our lever above, we can actually determine what I should get. So the ideal mechanical advantage, dE divided by dL, should be 2 as that length of the effort arm, so 2.0 meters, divided by 1.0 meters. I should get a mechanical advantage of 2. But we found we only got 1.8, which tells me that the system was not as efficient as it could have been. But it also allows us to find the efficiency of my lever. Okay, so I can go ahead and calculate the efficiency of our lever by looking at the ratio. So efficiency is going to be the actual mechanical advantage divided by the ideal mechanical advantage. And because efficiency is given to us in terms of percentages, we're going to multiply it by 100%. So let's actually go through and find out how efficient this lever on our page was. Okay, so my actual mechanical advantage we found was 1.8. The ideal mechanical advantage was 2.0. I'm going to multiply that by 100%, and I get 0.9 multiplied by 100%. Or we find out that this lever was 90% efficient. Okay, so that was one type of our simple machines. We could find the efficiency of it. Another type was our inclined plane. Okay, so for our inclined plane, if we think about an inclined plane, it has a height, which we'll define here. It also has a length. So the length of it is the how far I actually have to push the box or whatever object, my load, up that plane. So the ideal mechanical advantage for a inclined plane is given as the length of my inclined plane divided by the height. Okay, so this will be our definition for the ideal mechanical advantage if we're dealing with an inclined plane. Okay, so let's go ahead and do an example of an inclined plane as well. Okay, so an inclined plane, 5 meters long. So let's go ahead and draw this picture. So I have a 5 meter long inclined plane. That means that this length here, this length is 5.0 meters. And I'm trying to push a box up it. The height that it will get is 2 meters. So my height here is 2.0 meters, and this is my length. And I'm pushing a box with a force of 145 newtons. So I'll draw in here my box. So there's my box. My effort force is 145 newtons. And if I was going to lift this box, my load force would have been 343 newtons. That's if I was just going to lift it straight up in the height and put it right on top of my inclined plane. Okay, so you can see that I'm using a smaller force with a larger distance to get the same result. So that's the purpose of an inclined plane, is it reduces the force but increases the distance that I actually have to travel. Okay, so for this, what do we want to do? I want to find my actual mechanical advantage. My actual mechanical advantage, if we remember, is the ratio between the load force to the effort force. So I'm going to put in my load force and my effort force. So 343 newtons divided by 145 newtons. And I get a value of 2.37 as my actual mechanical advantage. So that's one of my answers. That is my actual mechanical advantage. I'm now going to try to find the ideal mechanical advantage. So ideal mechanical advantage, we remember, is made up of the length divided by the height for inclined planes. So the length path was 5.0 meters, and the height change is 2.0 meters. And if I divide that out, I should get 2.5. So it's telling me that my ideal mechanical advantage is 2.5. So I want you to notice something here. The actual mechanical advantage should always be smaller than the ideal mechanical advantage, because we'll lose energy as we use the machine. Okay, so the last piece here we want to work on is the efficiency. So we know that efficiency, and I'm just going to summarize it as EFF, is the actual mechanical advantage divided by the ideal mechanical advantage multiplied by 100%. So my actual mechanical advantage was 2.37. My ideal was 2.5, and we're going to multiply that by 100%. And I get an answer of 0.95 multiplied by 100%, or 95%. So my efficiency of this inclined plane was 95%. So I get 95% of the energy out of what I put in. It's telling me that I'm losing 5% of energy as I'm using this simple machine. Okay, so if you have any questions about what we've just learned, please don't hesitate to reach out to me. Otherwise, I'll see you soon.